This is our second video for our Unit 6 on energy, and it's called Kinetic and Potential Energy. It's probably a good idea to take some notes here, just to keep your thoughts organized and to help you on the video quiz at the end. What I want you to be able to do when you're done is to be able to describe and give examples of the different types of energy. You're going to learn about 6 different types of energy. We're going to use math formulas to calculate 2 types of energy called potential energy and kinetic energy. And I want you to be able to explain how objects can change their potential and kinetic energy. Energy is a weird thing because you can see the effects of energy, but you can't see energy itself. Physicists define energy as the capacity to do work. And in our last video about work and power, one of our parting thoughts about work was that work can transfer energy from one object to another, and that work can convert energy from one form to another. And to be able to talk about that, we need to know what types of energy there are. In the last video, we talked about mechanical energy, which we said was the energy due to movement or position. And then we broke mechanical energy down into 2 forms. Kinetic energy, that's the part due to movement, and potential energy, that's the part due to position. Today, we're going to look into these a little bit further. Let's start with potential energy. Potential energy, that's the mechanical energy that's due to position. Sometimes it's called stored energy. And under the category of potential energy, there are 3 types: elastic potential energy, chemical potential energy, and gravitational potential energy. Now what we're going to do is we're going to look a little bit closer at each of those 3 types, give a definition, and give some examples. Let's look at elastic potential energy. When you think of elastic, you might think of stretchy, and that's exactly what you want to think of with elastic potential energy. Elastic potential energy is the potential energy due to stretching. We said that potential energy is the energy due to position, so think about this as it's the energy due to something being in the stretched versus the unstretched position. And here are a couple of examples. One example is a slingshot, and if you've played Angry Birds, you know about that when you stretch back this slingshot, then that's going to put energy into the slingshot. It's going to allow the slingshot to be able to do work, in this case launching an angry bird. Elastic potential energy can be seen when you compress a spring or when you stretch a spring out. So when you move that spring to its stretched or compressed position, energy is being put into that spring and it can do work. And here's another example with a rubber band. When the rubber band is stretched, it gains energy and can do work, shoot something or shoot across the room. The next type is chemical potential energy. And how that's related to position is it's due to the position of electrical charges. If you think about a battery, that has energy in it and has the potential to do work. Fuel has energy in it, and your food has energy in it. And when we do work, sometimes we can transfer the energy of the food into the energy of something that we're moving. For example, when Tiger Woods did work on the golf club in the last video that we watched, he was converting the energy of his food into the energy of the golf club. The last type of potential energy is gravitational potential energy. And the definition's a little bit covered up here, so I'm going to write it right underneath there. It says due to relative height. So in this case, we're looking at the ball, and the ball has potential energy because of its height off of the ground. In this case over here, The roller coaster has gravitational potential energy because of its height off of the ground. Now there's a key word in here that I don't want you to overlook, and that key word is relative. If you look at the potential energy of this ball and the height of this ball, what are we talking about as our reference point? Are we talking about the ground that this young physicist is standing on? Or are we talking about the bottom here? These are two very different heights. If you're talking about the bottom of this pit, that's a pretty large height. And if you're talking about just from the floor she's standing on to the height of the ball, that's a pretty small height. So it's relative, and it's something that you need to think about. You can see an extreme case of that here. How much potential energy does this hiker have? Well, he has very little potential energy if you consider the height of this cliff right here, of him to this cliff, but he has a lot of gravitational potential energy if you consider the height relative to the bottom of the canyon. So it's all relative. Now that was a lot of information and a lot of new terms, so let's take a minute to get them organized and add to the diagram that we drew. Now remember, we had mechanical energy, which is all the types of energy we'll be talking about today, that can be divided up into kinetic and potential energy. And we just divided up potential energy into elastic potential energy, gravitational potential energy, and chemical potential energy. After you draw this on your paper, it might be a good idea to go back and add in the definitions of each of these right underneath. Another thing I want you to be able to do is to calculate the gravitational potential energy of an object. Now the gravitational potential energy of an object is equal to the work done to lift the object to its height. So the height is really important, and the work done is important too. Now remember, we said that work is equal to the force times the distance. And when you lift something, what's the force? That force is going to be the weight. And when you lift something, what's the distance? Well, that's the height that you're lifting it to. So in this case, we have potential energy, or specifically gravitational potential energy, equals the weight of the object multiplied by the height of the object. Another way we can write that same thing is mgh, or mass in kilograms times acceleration due to gravity, our friend little g. And remember, that was 10 meters per second squared, times h, which is the height, and that's going to be in meters. So what you'd get when you're done for potential energy, the units is going to be in joules. Now we've seen joules before when we talked about work. So the units for work and the units for energy are the same, and they're both in joules. At the beginning of this video, I gave you the definition of energy as the capacity to do work. So let's relate this to what we just learned about potential energy. So as the height of an object increases, that object is going to gain potential energy, according to that formula that we just looked at. As the height of an object increases, the potential energy increases. And since the potential energy increases, the object is going to gain the ability to do work. Now let's take a closer look at kinetic energy. Kinetic energy is the energy due to movement. So anything that's moving has kinetic energy. If something is still, it has no kinetic energy. There's a formula for kinetic energy, and I want to look at that now. Here it is. The kinetic energy equals 1/2 mv squared. I'm going to write that again just to make it clear. Kinetic energy equals 1/2 mv squared. Now let's break this down. This is kinetic energy, and that's going to be in joules. Equals 1/2 times the mass times the velocity squared. What are the units for these? The mass is going to be in kilograms, and the velocity is going to be in meters per second. So this formula and the formula for gravitational potential energy are ones that we're going to be playing around with over the next few days. Now a key thing that makes this formula different is this squared right here. 1/2 mv squared. What does this mean for us? Well, let's take a look. So in this formula, what does it mean if mass is doubled? Remember the strategy we used to solve problems like this? We said first you can plug in ones. So 1/2 times mass would be 1, and times velocity would be 1, but we square that. So when you put this together, it's 1/2. Well, let's square this first. 1 squared is 1, so this turns into 1/2 times 1 times 1, and that all multiplied together, 1 times 1 is 1, and then times half is 0.5. And if we compare that to what if the mass is doubled? 1/2 times 2 times 1 squared. 1 squared is 1. And now when we multiply all of these together, half of 2 is 1, multiplied by 1 equals 1. So if mass is doubled, the kinetic energy increases from 0.5 to 1. So the kinetic energy is doubled. Now what happens if velocity is doubled? Well, let's start with this again. 1/2 times 1 squared equals 1/2. Now what we're going to do is we're going to double velocity. So 1/2 times 1 times 2 squared. And now if we square 2, we get 4. And we multiply all of these together. 0.5 times 1 is 0.5, times 4 is 2. So what happens? Kinetic energy goes from 1/2 to 2. And if you run that through your calculator, you'll see that this means that the kinetic energy has been quadrupled. So there's a much bigger jump when velocity changes compared to when mass changes. Relating this back to the beginning where we said that energy is the capacity to do work, what we find is that when an object speeds up, when it increases its velocity, the object is going to be increasing its kinetic energy, and it's going to be gaining the ability to do work. Now that's kind of hard to understand, so I was looking for an example. What's an example that's something that speeds up gains the ability to do work? And I thought of a perfect one. A wrecking ball. And I'm not talking about this type of wrecking ball. I'm talking about this type of wrecking ball. So, when that wrecking ball gains speed, it's going to gain kinetic energy. And that's going to mean it gains the ability to do work. What type of wrecking ball can do the most damage? A wrecking ball that's moving at a higher velocity. Although this wrecking ball has done some damage recently too. Now a cool thing about kinetic and potential energy is that they can be converted to one another. Remember, we said that work is going to transfer energy from one object to another or convert energy. This is what I was talking about when I said convert energy. Now imagine that this young physicist that we've seen before, that's standing on this ledge, drops the ball down into the pit. Now what happens is when the ball loses height relative to the bottom of the pit, the height decreases, so the potential energy is going to decrease as well. What happens to that potential energy? Well, now this ball is in motion. So the potential energy that's lost here is going to be transferred to kinetic energy increasing. Since the ball isn't moving here, the kinetic energy is going to be 0. Here's another example of the same thing. This man has a big ball on top of the hill, and this is when it's going to have its most potential energy. But since the ball is still, the kinetic energy is going to be 0. As the ball moves down the hill, it's going to lose potential energy, but it's going to be speeding up, so it's going to be gaining potential energy. And at the very bottom of the hill, when the height is 0, potential energy is going to be 0, and the ball is going to be moving at its fastest, so the kinetic energy is going to be maximum. Let's take our video quiz and then let's practice these concepts by working through our problem set.